All right. In the previous video, we said here we are going to discuss something very important called the bias-variance trade-off. Bias-variance trade-off. So I might call it variance. Some people call it variance. It's just pronunciation, right? So we saw that our test MSC has a U shape, right? Test MSC. We saw that it has a U shape. And it turns out that this U shape is a result of two competing properties of all statistical learning methods. What is it? What are those two? Here I'm just going to give you a mathematical equation, but you don't have to know what it means or how to derive it. We are going to just take out the implications of the equation itself, right? So it's possible to show that test MSC for any given x naught or observation that we have never seen. So for any new observation, it is possible to show that the test MSC is the sum of three fundamental quantities: the variance of the predicted value, the squared bias of the predicted value, and the variance of the error terms. Let me write that as a mathematical equation here. So the expected test error, so this is the test error that we expect, right? The expected test, or this, yeah, the expected test error, test MSC, it is equal to the variance of the predicted value plus the square of the bias of the predicted value plus the variance of the error terms. You can show this mathematically, but that's not the point of this course, right? This course, if you watched my introductory video, I said there are some equations I'm going to write without explaining them, without deriving them, but we'll try to explain what they're saying. So this formula here looks scary, but let's just dig deep into what it is saying, right? So this is okay. Let me write what the terms are. So this part here is the expected test MSC. Cool. This is the variance of the predicted value. So it's just going to be x of the predicted values. Cool. And this is going to be the squared bias. Squared because you see here we are squaring it, right? Squared of bias of f of the predicted values plus the variance of the error terms. Variance of error terms. Perfect. So from this equation, let's just say, what is the point of predicting? We want to be accurate, right? We want our models to be accurate. But what does it mean to be accurate? It means this test MSC has to be small, or it has to be minimal, right? That's what it means to be accurate, which means we are predicting very well. So what we are basically saying is we want this expected test MSC to be minimized, right? We want this to be minimized. But for it to be minimized, what it then means is we need a statistical learning method that simultaneously minimizes the variance and the bias, right? That's what it basically, this is a constant, so it falls off. So we want a statistical model that achieves low variance and low bias. If we can get that model, it will lead to a minimum error, minimum test MSC, and our predictions are accurate, right? Cool. So as we can see, okay, variance inside it carries like some squared values. So variance is always positive. It is a non-negative quantity, so it can be zero or or positive. Let's just say positive for now. And then the squared bias can be, because it is squared, the bias itself is squared. The bias is being squared. So which means this quantity, the squared bias, is either 0 or positive. So let's just call that positive. What this then implies is that this expected test MSC can never lie below this variance here. It can never lie below the variance, right? If you move everything to one side and then you work with the variance and try to see this, what is this thing called? This expected, because it's going to be E and then minus the var. I'm getting into maths, though I just said I don't want to get into maths, but let's just quickly see here, is equal to var E, right? And we know this is a positive quantity and we know this is a positive quantity. So if they are equal, it means this, even after subtracting positive quantities, it is still equal to this var. You get what I mean? This is a positive quantity and we're subtracting it from E. And we have another positive quantity that we're subtracting from. It means this is a very large number compared to this var. So our expected test MSC will never lie below this. It will never be smaller than this var, the variance of the error terms. And the variance of the error terms, they have another name that we have been using called the irreducible error. It's the error that we cannot get rid of. It's the irreducible error. So it means the expected test MSC, it will have that. You remember in our previous graph with the dash line, and then our test MSC was like this. It will never lie below this dash line, which is the irreducible error or the variance of the error terms. Perfect. I hope I explained that well. So when we're talking about this variance of f of the predicted values, variance is the amount by which f would change if we used a different training data set, right? So our predictions here, variance of this fx x naught, right? How is it going to be different if we used another different test set? You remember when I gave the example of 1 to 8,000 as our training set, right? Someone could have said, okay, I have 10,000 observations. Cool, this person uses this training set from 1 to 8,000. Someone could have said, okay, I'm going to use the one for 2,000 to 9,000. And someone could have said, I'm going to use the 3,000 to 7,000 to train my data, to 10,000, I mean, to train my data. A person could have not 2,000. Let me just say 2 to 9,000. I'm trying to get the same ranges. They're not going to be, definitely not going to be the same. If you're doing a 1 to 8,000, then another person, if you're going to use the same number of observations for training, another person could have said 2 to 8,001. And another person would have said, maybe I'm choosing values, observations from number 3 to 8,002. You get what I mean? So there are so many different permutations of training data. And what happens in our, if you remember, our linear model is something like this: b0 plus b1x1 plus b2x2 plus whatever it is to b p xp, right? These b's, the betas here, these coefficients are calculated using our training data. If you remember, they're calculated using our training data. If you don't remember, don't worry, the linear chapter focusing on linear regression is going to come. We're going to cement these concepts. So these betas are calculated using, or are estimated using, our training data. So which means someone who uses this training data set might get slightly different betas from someone who used this training data set, and someone who used another training data set. So those differences, they lead to this variance. Variance is the amount by which f would change if we used a different training data set. Pretty much that, right? So high variance, what does high variance mean now? High variance means small changes to to our training data. Small changes to training data can result in large changes. So small changes in training data can lead to large changes in our F, right? Because this thing is what we call high variance. So any small change in the training data, if it is high variance, it means any small change in our training data can result in large changes in F. So generally what happens is more flexible methods have higher variance. So this is important to take note of. More flexible the method, the higher the variance. Because when you are becoming more flexible, remember that wiggly line from the previous video. It was following the data very closely. Like our points were like this, and this model was going around following each data very, very closely. And when it follows the data closely, it means it is more flexible, right? But what is the implication of changing the training data set? Now, instead of having the training data set that is like this, right? That is our training data set, and this model is following. It is a model that follows the data points. What about when we now have training data set that is like this? Can you see now? If it is a model that is more flexible and follows all the data points, our new model is going to be like this, and it's very, very different from the original one that he had. So someone who uses a different training data set to the one that has been used before will get a different F if our model is very flexible. You see that from this example here. So which means a very flexible model will lead to higher variance. So let's talk about bias. So so this is important. That is what variance is. So let's talk about bias, right? But what is this bias that we're talking about? So bias, it refers to the error that is introduced by approximating a real-life problem. Okay, let me write some main points. Bias introduced by estimating a real-life problem using a simpler model. Or let me just say a simple model. What I mean is, in real life, things are so complicated, right? Things are so complicated. Imagine there are machine learning models that predict the cancer diagnosis. But the cancer diagnosis could be, getting cancer could be dependent on so many different factors. Where you live, the food you drink, the water, the food you eat, the water you drink, exposure to the sunlight, how much sunlight you got exposed to, all many different X's. The X's that that could affect your cancer diagnosis. But some of them could be very difficult for us to even measure. But we can create a simple model to say, okay, these are the main factors that we're going to look at. Do you smoke? Do you drink? Do you do the behaviors that we want, right? And then we can create a simple model to try estimate the cancer diagnosis, right? Or just look at, in a field called computer vision, we can look at your cells in your body. And then if we see some particles in there, we'll be like, yeah, this is the cancer diagnosis. You get what I mean? But we're using a very simple model. It's not simple, but it is simple compared to the actual model in real life. So when we introduce the estimation of a real life phenomenon using a simple model, we introduce bias. We introduce the error of bias, right? For example, when we use like a linear regression, very few things in real life have a linear relationship. So by using a linear regression, I'm not saying it will not work, it will not give us good results. It might give, in many instances, it gives us good results or a good idea of what's going on in our data. Linear model works, but then it will work with some bias because the actual data, very few things work in a linear fashion. Cool. So now we now know what this equation is saying. The equation is just saying the test error is composed of the error that could be from our training data, and the error that comes from us simplifying real life phenomenon. And then the other irreducible, that in our training data set we didn't measure things we were supposed to measure, or things we could never ever measure, the irreducible error. I think it makes sense now, right? So now so generally, let's see if I have enough space. I don't have enough. Okay, I think that should be enough for us to finish this video, right? Yeah. So let me delete everything and just start up there. So generally what we are saying is, as we use more flexible methods, right, as flexibility increases, variance increases. What happens to our bias? Our bias is going to decrease becoming more non-linear, or becoming more complicated. So flexibility increases the complexity of our model. It increases the complexity of our model, and it will get closer to real life. So bias decreases, but our variance increases, right? So as flexibility increases, the relative rates of these changes of variance increasing and bias decreasing will affect our test MSE. They will affect our test MSE, right? Let's look at what happens here. So as we increase our flexibility, what happens is when we increase our flexibility, our bias initially decreases very, very fast. Bias decreases very fast. It does something like this. It decreases very fast, right? So this is going to be, let's say, our squared bias. And our variance is going to increase slowly, but as flexibility becomes way too much, it now becomes too flexible. It's now following the points way too closely. So now this becomes our variance, right? In the beginning, what is the, you know what I mean? Like y is equal to beta naught plus beta 1 x. Not very flexible. We're still down here. There's not much variance there. There's not going to be much variance there. But if we introduce another beta 2, beta 3, when we're now getting to beta 100, it will now start following the points way too closely. Because this is a straight line, right? So it's a straight line like that. So there's not much variance there. There's not much flexibility there. But when we start introducing beta even to 100, then that's when we start following the points closely. Flexibility is high, and then the variance goes up like that. Cool. So now, what happens to test MSE? We know that our test MSE is the summation of these 2 points here. So if our test MSE is the summation of the 2 points, its shape will be something like this. It will be something like this. So this becomes our test MSE. So as flexibility increases, bias tends to initially decrease faster than variance is increasing. Therefore, our test MSE declines. It declines, cool. And then at some point, increasing flexibility at this point here, increasing flexibility has little impact on our bias because our bias is now down there. We are now following the very complex model in real life. So there's very little bias anymore, right? There's no more impact on bias. But now we are becoming the variance is now increasing because we are now starting to follow the trends of the data, or following the points too closely. So our variance now starts increasing, right? So the test MSE now starts to increase. Our test MSE now starts to increase as we add up the variance and the variance and the squared bias. So this relationship between bias and variance, that is what is called the bias-variance tradeoff. The one that we have just shown here. The one we have shown here in this graph is the bias-variance tradeoff. Right? So a good test set performance requires low variance and low squared bias. That's what we want. We want a model that will give us low variance and low variance, low bias, right? But the trade-off, because it is easy to get a method with low bias but high variance, or a method with low variance here but high bias. So the challenge is finding a method for which the variance and the squared balance are low. Finding this one here. That is the challenge. How do we find a model that lowers the low variance and low bias? Finding that model, that is the challenge of predictive modeling, right? So yes, I've discussed a very important part of statistical learning. We are going to reference this, but we're not going to explain it. So these videos, last videos of this chapter, they are a bit long because we're talking about things that are going to be very important later when we're choosing our models, right? We're going to just reference them and then move on, but we needed to emphasize them in this chapter. We are going in the next video. We are going to do the last part. I think it's the last video before we do a lab. We're going to do the last theoretical video where we just discuss. Here we're looking at linear regression and regression in general. What about in a classification setting? Remember, we said our machine learning, our supervised learning, is divided into regression and classification. So here we talked about the errors and how to measure how well we're doing in regression. What about when we're in classification? How do we measure that? We're going to see that in the next video.